Okay. Hi. Sriram, can you confirm if I'm audible? Just type in the chat. Yes, if you're able to hear me, or just unmute and say,
Yes, yes, sir. I'm
okay,
hearing.
fine. Then it's fine. So I guess we should start. It's already 5. Welcome to the week 8 live session of NPTEL NOC24 EE-143 tutorial. Uh, the course titled Semiconductor Devices and Circuits, taught by course instructor Professor Sanjeev Sambandhan. I am Yavar, the TA for this session, and as has been the case since past many weeks, the schedule for my sessions is every Sunday 5 p.m. to 7 p.m. You can reach out to me on email, or you can just browse my homepage if needed. Let's quickly go over through the guidelines. In case you have any query, you can write that in the chat window. Okay, you can just type your query in the chat window, or you may just raise your hand. And please make sure that your microphones are muted, especially when you don't intend to speak. Uh, and I would appreciate your cooperation for making this session an interactive one. And I'll assume that you have pen and paper along with you. Uh, and also you should have a calculator for calculations. The session recording link and lecture notes will be shared by the NPTEL course team in the due course of time. Okay, so the prerequisites include the last week's lectures that covered the following topics: metal oxide semiconductor capacitor, MOSCAP, MOSDOT by the instructor, and we also, studied the CV characteristics, right, of MOSCAP. So any doubt with regards to MOSCAP or its CV characteristics? Should we have a short discussion? That depends if you have a doubt or not. There is only one student in the session live, so if he has doubt, we may discuss that, or otherwise I'll continue with the problems. So Sriram, should I head over to the problems?
Yes, sir.
Okay, fine. So the first question is, which among the following statements is true with regards to an ideal MOSFET with a p-type semiconductor? Okay, so you have a MOSFET with a p-type semiconductor. Which among the following statements is correct? This is a simple question, and I assume that one of you would be able to answer it. So please type the answer in chat or just directly let me know by mic. So the first option is in accumulation mode, the semiconductor insulator interface. It has a hole concentration that is equal to the electron concentration in the bulk. Okay, so is that the case? That is not right. Although in accumulation, holes do accumulate at the interface, but it's not necessary that the concentration would be equal to the electron concentration in the bulk, right? They are free to, be more than that, right? So the second option is the high frequency characteristics. They are observed when the frequency is higher than the electron generation rate in the depletion region. So is this correct? First of all, what happens? I mean, how do low frequency characteristics look? Anyone? So the question that I'm asking is, how do high frequency and low frequency characteristics look first? Because only then we'll be able to answer this question, right? So this is a p-type semiconductor, right? So let me draw how. So suppose, I mean, the high frequency characteristic. First, let's draw low frequency characteristics. In this is how the high frequency characteristics would look. Right? Something like this. And had it been, I mean, had the frequency been low, typically around 1 to 10 I mean, 1 to 10 hertz, then this would have been something like this. Fine. So this one, I'm saying that this is low frequency, right? Typically 1 to 10 hertz, right? This is your CGB, right? I mean, we only have two terminals in MOSCAP, so this is CGB in farads. And this is your, let me, if I draw this one, right? This is your moderately high frequency, right? Kilohertz or more. This is your VGB. and this is your depletion region, right? This is your accumulation, right? Similarly, this is your depletion, I mean inversion. This is roughly Cox. Is this fine? Prasad Rao, you are unmuted. If you don't intend to speak, I'll mute you. Fine, fine. Okay. So now the second point is that the high frequency characteristics, they are observed when the frequency is higher than the electron generation rate in the depletion region. That is the case because when the frequency is higher than the electron generation rate in the depletion region, uh, I mean, uh, the charge don't get enough time to build up, right? I mean, that's why this curve doesn't go up till Cox and instead it remains here, right? And this is the reason for that, right? So that's why this one is correct. Let's go through other options. The deep depletion characteristics, they are observed when the frequency is lower than the electron transit. Hold on, looks like something went wrong. I'm audible, right? Why did I get message that Stephen, Prasad Rao, anyone among you, can you, confirm if the screen is visible and I'm audible? Should be the case, but still. Can we proceed? Sorry. What about deep depletion? I guess the network is little poor today. Fine. Just interrupt me if we can hear you fine, then it's fine. I was actually continuously getting prompts that, I mean, there is a poor connectivity, so it might affect the quality. That's why I asked. Fine, if you are able to hear me, then it's fine. You would be recording fine then. So yeah, this one, this is the correct option. How do deep depletion curve, how does that look? I mean, it just continues, right? Right, this one is your deep depletion. So when do we have deep depletion? I mean, what is the condition for that? Anyone? Okay, so generally we have quasi-static measurement, right? I mean, where when you stop at any step of VGB, right? I mean, and then we give sufficient amount of time for the sample to equilibrate, right? And then we perform the measurement. Uh, on the other hand, if we measure the CV characteristics when your this frequency is very high, right? And VG is swept rapidly, right? So there are two conditions. First one is that your frequency should be high, right? And the other one is that your VG is swept rapidly, right? Then we, then we move to a non-quasi-static state, and that is when this deep depletion characteristics are observed. Fine. So, yeah, that is pretty much it. So this one is actually incorrect. That is what I meant. So the last one is the low frequency character is obtained when MOS capacitor avoids entering depletion region. No, it does enter depletion region. The thing is that when the frequency is low, uh, uh, the characteristics would look something like this. Okay. Why does it look like this? Why does it come back? Because the process can keep up with the time, right? Because since the frequency is lower than the electron generation rate in the depletion region, this whole process can keep up with time. That leads to higher value of the inversion capacitance, and this CGP goes back to COX, right? Yeah, that finishes the first one. Let's move on to the second. I want you all to try this one. This is easy, and I expect you all to answer this. So a MOS capacitor is constructed using a p-doped semiconductor with intrinsic concentration of 10 to the power 10 per centimeter cube and dopant concentration of 10 to the power 16 per centimeter cube. In strong inversion mode, the surface potential, the insulator semiconductor interface has a value dash volt. You need to answer this. So the question is asking you to compute the value of the surface potential in strong inversion, right? So what, I mean, surface potential is equal to what in strong inversion? Anyone? Please speak up or just write in the chat that we don't know, because otherwise I'll assume that you know and I'll wait. See, I need to obtain the size Okay, I mean, disconnected for a while. So this is what you need to find, right? Size in strong inversion. What is this? 5. Have you seen this? This 5 is the bulk potential, okay? This is equal to KT by Q ln of your Na by Ni, since it's a p-doped semiconductor. All right. So when the surface potential, and what is this 5? Okay. Suppose this is your EC, this is your EV. If this is your EI, right? Today this is unstable. Your your 5 is this, right? This is your 5. I mean, since 5 is potential, so Q5 would correspond to the energy. So this is actually the energy difference between EI and EF. So when psi s is equal to this 5, the intrinsic, see, why is it we are trying to get you back into the meeting? Am I leaving the meeting? Am I leaving the meeting? At least let me know. I mean, at least I am getting the prompts that will join you back in the meeting. At least type that I was in the meeting. I did not leave. So I'll from now on ignore those prompts. Did I leave the meeting briefly? Yes, no, no. Okay. From now on, I'll be ignoring those prompts. Okay. My screen actually turns blank and I get a prompt that will join you back in the meeting. I'll be ignoring that now. Okay, now, when you start applying bias, right? This, I mean, band bending occurs, right? So a point would come when, suppose this is your interface, right? When EI becomes equal to EF at the interface, okay? I mean, surface potential is band bending, right? If we apply a bias that is, I mean, high enough that EI reaches EF at the surface. So in other words, your surface potential psi s is equal to 5. That corresponds to weak inversion, right? This is weak inversion, or you can say the upper limit of the depletion. Okay, onset of weak inversion or the upper limit of depletion. You can call it either thing. So what happens is at the surface, the surface is intrinsic. Okay, that is the key point because your EF is your EI at the surface, right? That's why the surface turns intrinsic. So the surface potential corresponding to which this happens is 5. But in the question, we have been asked that to compute the surface potential size when this EI, I mean, when strong inversion mode happens. So what does, I mean, firstly, you should know that in strong inversion, the EI is below EF at the surface as much as it is above the EF in the bulk. What I mean by that is falling. So our diagram would change a little, right? Right. Something like this. So would be Q5 here as well. Okay. So it's, I mean, uh, here EI was above EF by Q5. Here EI is below EF by Q5. So what is surface potential then, Sias? If this state corresponds to, if this state corresponds to your, what should I say, strong inversion, then what is this surface potential? Your surface potential would simply be sum of the two, right? So your surface potential would be your, this would be 2,5, isn't it? This would be 2,5. So this would be then equal to 2 kT by Q ln of your Na by Ni. Fine. Let's compute that. Is this clear what I just did? I'll assume it is, otherwise you would have interrupted me. So now listen, this would be your 2 times your kT by Q is 25 milli, right? And your this, what should I say, ln of your Na by Ni, right? Na by Ni is 10 to the power 16 by 10 to the power 10. 10 to the power 16 by 10 to the power 10. This is 2 times 25 milli into ln of 10 to the power 6, right? Your size would be equal to 2 into 25 milli into 6 ln of 10. Correct? So this psi s would be equal to 0.69 volt. That is your answer. Fine. If this is clear, we can move on to the next one. Question third, right? So in question third, we need to find this relative permittivity of the semiconductor, right? We need to find the approximate value of that. So yeah, the CV curve for the MOS capacitor is shown. The MOS capacitor has area 100 micro cross 100 micro, and it's constructed using a p-doped semiconductor. The intrinsic carrier concentration can be taken as 10 to the power 10 per centimeter cube, and dopant concentration can be taken 10 to the power 14 per centimeter cube. Uh, yeah. So the scale is picofarads. Thermal voltage is exactly 25 millivolts. So we'll take that as the value. for this problem. The permittivity of the vacuum is 8.85 into 10 to the power minus 14 farad per centimeter. Okay, so this is how we will proceed. Firstly, we'll note the quantities that we already have. For example, A, that is 100 micrometer square, right? That is equal to 10 to the power minus 4 centimeter. Is it? Yeah. Just correct me if I'm wrong anywhere. Your Ni, that is equal to 10 to the power 10 per centimeter cube. Then your this, what should I say? Your Na, right, is 10 to the power 14 per centimeter cube. Your Vt is equal to 25 millivolts. Your epsilon naught, that is 8.85 into 10 to the power minus 14 farad per centimeter. Psi s is equal to phi f, right? Okay. I mean, we'll consider this point, right? Because this would correspond to the case of the maximum depletion, and and we know that happens at your this onset of weak inversion, or I should say, the upper limit of your depletion region, right? Psi s is 5. So this would correspond to the case of your max depletion. So if that is the case, what is your psi s is equal to? Your psi s is equal to your phi f, and that is equal to kT by Q ln of your Na by Ni, right? That is equal to 25 milli times ln of what is your Na? 10 to the power 14. Ni is 10 to the power 10. So your psi s is equal to 0.23 volts, right? Done. What about now C effective? I'm interested in this case, right? I know that the C effective is 1 over 1 by Cox plus 1 by your C dep, right? And that is equal to, I mean, see, this is your 0.1, 0.1, 0.2, 0.3, and this 0.3, right? So I'll take it 0.3, your picofarad, right? And what about your this Cox? Your Cox is 2 picofarads, right? That is your Cox. So what is then C dep? C dep is, okay, I will write that C dep, we can compute it, right? See, I know this C effective, right? I know this C effective. I know this C ox, these two are known. This can be computed because overall quantity we know is equal to 0.3 picofarad. So then what is equal to this C dep? This would give us C dep, right? This I'll leave as an exercise for you. This will obviously be a little higher than 0.3, right? Because capacitors in series, the equivalent capacitance, if that is some particular quantity, the individual capacitance, they both are greater than the equivalent capacitance, right? So that's why CDF would be little greater than 0.3. Here, it turns out that this is 0.35 picofarad. How this comes about, you'll figure it out, okay? Now then, wait. C dep by A, right? Your C dep by A is equal to square root of Q epsilon is Na whole divided by 2. Uh, Here you need to, I mean, substitute the surface potential, which in our case would be 5, right? So what is C? Okay. This means that your C dep by A whole square of that would be Q epsilon S Na whole divided by 2 psi s, right? Then, yeah, then we'll do some manipulations. Your C dep is your 0.35 picofarad, right? So I'll write 0.35 into 10 to the power minus 12 whole divided by your area. Your area is 10 to the power minus 4 centimeters square. Is it 100? 100 times 100 is 10 to the power 4, and then we have 10 to the power minus 12, that is 10 to the power minus 8, and then 10 to the power minus 4 centimeters. I guess it's fine. You can just correct me if you think I have made any mistake somewhere. What about this? Then what I'll do is I'll leave this epsilon s here and I'll transfer s to the quantities, right? I'll take 2 there, this here, and this here. Only this will remain here. So we'll have something like this. 2 psi s whole divided by QNA. That is equal to your epsilon s, which is equal to epsilon naught K. Here K is the relative permittivity of this material silicon. I mean, of this material. K we don't know, in fact. It's not silicon, right? We only have been given that this is some semiconductor. That's it. So now what? We'll substitute the values. This would be 2 times your surface potential, that is 0.23, right? Whole divided by your Q, that is 1.6 into 10 to the power minus 19. times your Na, that is 10 to the power. Na is your 10 to the power 14. Now your epsilon naught is 8.85 into 10 to the power minus 14 farad per centimeter, right? So if you then substitute, I mean, solve this and solve it for K, you'll get K as 3.95. Okay, just verify it. Verify this at your own end. So this is 3.95, right? This is this clear? Yes, no, no. Okay. Stephen, I mean, I missed your this message. What was this no corresponding to? I'll assume this was not corresponding to this one. How did you get C effective? Okay. See, this your C effective is this capacitance, right? This capacitance. The value of this zero point 0.3 picofarad I got from the plot. Why? Because till here it's zero point 0.5, right? And from 0 to 0.5 it has been divided into 5 parts. 1, 2, 3, 4, 5. And this corresponds to this one. So this has to be 0.3. Is this clear how this would be 0.3 now? Hmm? I mean, I did not get this. Do you mean yes or what? Okay, fine. So you are convinced, right? So that addressed your this query. This is fine, right? After that, this is clear how I reached here. Or should I mean, again, briefly explain to you? Understood. Fine. So with that, I mean, we can start with, I mean, next problem, which is the problem 4. An ideal MOSCAP that is fabricated on a p-type silicon substrate has a doping concentration of Na that is equal to 10 to the power 16. The value of the work function phi s of the silicon substrate at room temperature is what? That is, this is actually a very trivial question, and I assume you will work it out. I'll give you 3 minutes, okay? Just figure it out. Okay, so any update? See, this one was easy. Let me solve it. You were provided NA, right? And your NA was 10 to the power 16, right? Bias we're supposed to find. The rest of the quantities were given, right? For example, EG was given, uh, electron affinity chi was given, Ni was given, right? So now, firstly, we'll compute phi f, the bulk potential, which would be your kT by Q log of this Na by Ni, right? And that is equal to your 26 milli times log of 10 to the power 16, 1.5 into 10 to the power 10, right? Your phi f is equal to 0.35 volts. Then what about this work function phi s? Your phi s would be the affinity plus Eg by 2q plus phi f, right? Something like this. First, you'll have this affinity, then this Eg by 2, and then this q phi f. And this particular quantity is your work function. That's why. So you'll write phi s is equal to our affinity is this one, right? So this would be 4.05 plus Eg by 2q would be 1.1. Your phi f would be 0.35, right? Your phi s would be equal to 4 point, sorry, this is 1.1 by 2, right? So turns out this would be this much, right? 4.95 volts. What about, okay, so work function is Q times phi s then. So your Q times phi s would simply be 4.95 electron volt, right? What about the next one now? Problem 5. So if phi ms is equal to 0, we need to, I mean, say what this phi m is in terms of chi s, Eg, and E, phi f, right? I'll wait for a couple of minutes or 3 minutes and Okay, so your phi m would be equal to C. Since phi m is phi s, because uh, it's given in the question, right? Phi ms is equal to 0. So this is equal to this. In other words, this is at a constant level. So in terms of this, and this, I can say that this phi s is equal to your chi s plus Eg by 2 plus Q phi f, right? So which option is correct? Option A, right? Clearly it's option A. Then you have this problem 6, which is in accumulation mode, the net capacitance is. In accumulation mode, your net capacitance is equal to Cox, right? This is Cox, accumulation mode. Right, so we'll write that in accumulation. We'll take this one. This is clear, right? I'll take that as a yes. Now problem 7. Problem 7 is we can have a look and I'll wait for 2 to 3 minutes. Okay, attempt this one. Okay, I guess that was sufficient time. Problem 7, right? So your Cox. See, we need to compute the threshold voltage of this MOSCAP, right? And yeah, your Cox is epsilon ox by Tox. That is equal to your I mean 3.9 into 8.854 whole divided by your Tox, which is right. So this comes out as 3.45 into 10 to the power minus 8, your farad per centimeter square. Fine. Now, what about VTH? Your VTH is your 5 ms plus 2q epsilon s times 2 phi f Na, right? Square root of this times divided by Cox plus 2 phi f. Okay. What is 5 ms? Your 5 ms is equal to your 5m minus 5s, which is equal to your 4.1 minus your 4.95. So your 5ms would be equal to your minus 0.85 volts. So if you'll plug these values, right, I mean, if you'll plug this one here and put in the values, you'll get the VTH equal to you'll get VTH equal to minus 0.85 plus 2.11 volts. Your VTH is equal to 1.26 volts. What about now problem 8? In your problem 8, your ideal MOSCAP is given with, D equal to 20 nanometer. Na is given. It's operating at 300 Kelvin in a state of inversion that is exactly halfway between the intrinsic and strong inversion region. So see, intrinsic would correspond to your psi as being equal to 5. Strong inversion would correspond to your, sorry, to your this, what should I say? To psi is 2 5, right? So psi is equal to 1.55 would be somewhere in between, right? And we are interested in that. So your the psi is equal to 1.5 kT by Q. ln of Na by Ni. Yeah, that's pretty much it. I have 1.5 into 20, I mean 0.0259, right? Times your ln of your Na, which is 10 to the power 16, whole divided by your Ni. Ni would be equal to 1.5 into 10 to the power 10. Psi s would be equal to your 0.54 electron volts, right? So I mean, applied voltage to achieve this state would correspond to this one, right? 0.54. So yeah, that's it. That was the last problem of today's session. If you have any doubt, you can ask. Otherwise, we'll wrap it up here. So does anyone have doubt? Yes, no. Was it clear? No response? Okay, Stephen is typing. Can you explain how phi s value changes? Phi s, uh, phi s or psi s? Are you talking with respect to the eighth question? Okay, it's with respect to the eighth question. So I guess you are saying, I mean, how this size changed from 5f to 1.5f, I mean 1.5 times 5 to 2 times 5. Is that your question? Is this your question? Okay, so the thing is we apply bias, right? When we apply bias, we can invert the surface, right? I mean, as I showed in one of the previous problems as well. So when the applied bias is such that surface potential corresponds to phi f, that would correspond to intrinsic state. If we move beyond that, a point reaches when, wait, I'll use this. If we move beyond that, a point comes when this applied bias is sufficient enough that this psi s is 2 phi f. Okay, that corresponds to strong inversion region. This is the intrinsic. It's all I mean, bias control. Okay, you increase the bias, you'll attain more and more inversion. Although it would ultimately get pinned at some value, 2.5 or slightly greater than that. But the idea is surface potential is a function of this VGB. So as you increase VGB, your surface potential increases. Is this clear now? In fact, uh, you'll find uh, VGB. Okay, size is given, you'll find corresponding VGB. That is left as an exercise. Okay. Would it be 0.54 or will it be some other value? That I'll be leaving as an exercise for you. Let me know. Okay. This in fact would not be, this would be volt, right? Find it. And if not, then I'll take this up in the next session. Is it fine? Should we end the session then? I'll take the silence as yes. So thanks for tuning in. We'll be ending the session right here. Okay. Okay. Thank you. Bye.